Okay, here's our fourth and final conic section, the hyperbola. So it's the set of all points xy on the curves where the differences of the distances between the foci is constant. So it's kind of the same idea of the ellipse, whereas if you added the two distances together, that would be a consistent number like 17 or 28 or whatever. Whereas this one, you're actually going to subtract the distances, of course, making sure that it's positive. Basically what we have here is it's actually pretty similar looking equation to the other ones. So we have our center, which is still identified as HK. That's not different. We also have our vertices this time still identified by A, and that is that A distance right there. Vertex is that location, and then the vertex is this location as well. Now, do keep in mind, just like with the ellipse, it could be, stretched more vertically or horizontally. This one, it can actually open vertically or horizontally. In this case, it's opening horizontally, which means that the A distance is from the center right and left to get to each of the vertices. There are no co-vertices here. We don't have that. But we do have that distance of A to get to the vertex. Then we still have our foci. Notice the foci this time, though, are further away from the center. So we're going to keep that in mind. We also still have this distance of B, but in this case, what we're dealing with here when we use A and B, so this distance here, it actually gives us this point up in that corner, all of these corners of this box. What that does is it gives us the equation of the asymptotes. So we'll get into that in just a second, but we still have A, we still have B, we still have C. It's just that we have a small change to the equation, and we now have asymptotes involved as well. Okay, so I'm going to go back to the whole idea of, well, how do you calculate C? Well, previously, when we did the ellipse, if we wanted to go through and calculate the distance using the A squared and the B squared, we subtracted them because we needed the C to be like a smaller distance than A was. Well, not the case this time. This time, if we went through and we used our A and B in our equation and we calculated that distance of C, we actually want the C to be further from the center than the vertices. So in this case, we aren't going to subtract, we're actually going to add. So what you see down here at the bottom when you're trying to calculate the location of C is because we want the distance to be greater than both A squared or A and B. So it really does just look like the Pythagorean theorem here. Okay, so types of hyperbolas. Okay, so I did say that they could open horizontally, so they open in the x direction, or they could open vertically and they open in the y direction. So we take a look at this. We take a look at the equation. There's one glaring difference from the ellipse, and that is that we actually have a minus sign now. We don't have an addition. So the big difference right there is that minus sign between the x squared and the y squared. For me, I know that instead of the two pieces coming together, so to create one thing, that the minus tells me that I'm actually ripping them apart. So I'm sending them in opposite directions from each other. It doesn't matter which type of a transverse you're talking about. Transverse just means which way does it open. It's still going to be a subtraction sign between the x squared and the y squared, whether the x squared or the y squared comes first. Okay, now the order in which they occur does matter. So we know that addition, it doesn't matter if x squared comes first or y squared comes first, but with subtraction, it absolutely does matter. And so we take a look at the A squared, and I want to take a look at just the very first thing that is showing up, and I want it to be positive. We take a look here. A squared is always going to be on the bottom of the first fraction. Always. Whatever variable is in the top of that fraction tells you which way this thing opens. So what I know here is that this opens in the x direction. and I can see it in the other one as well. So if I take a look at the vertical transverse, I see that a squared is in the bottom of the first fraction. I also see that that first fraction, and first I mean it's the positive one. You want the subtraction to happen between them. If this is y, this is telling me it opens in the y direction. So whoever comes first, whoever's positive, that's the direction you're opening in. The center is still the same. That's not going to change. It's still HK. Remember that H is associated with X and K is associated with Y. So pay attention to which number is with which variable. And then the asymptotes. Okay, so we want to be able to write the equation of a line, which is ultimately what this thing is. So if I take a look at the asymptotes here, it doesn't matter which one you look at. I want it y minus k is equal to plus or minus slope x minus h. That's it. The slope, though, if you remember, so my little tricks for remembering things. I remember that slope is always rise over run. I know that the rise is the change in y's over the change in x's, so rise over run. So I just pay attention to who's underneath y, and that goes on top. So if I take a look back here, I know that in my very first equation, I'm looking for who's underneath y. Well, who's underneath y is the b squared, which means my slope here is going to be the change in y over the change in x, which, well, underneath the y is the b. Underneath the x, or the run, is the a. So there's my slope. Make sure that you square root them. Okay, I'm going to do the same thing here. I know that that's going to be slope, which is the change in y over the change in x. I find who's underneath the y first. So I'm going to use a over who's underneath x second, b. So I always use what I know about slope. Also, my number one recommendation with this when it comes to your slopes, do not simplify the slope. Even if you can, I still wouldn't do it. Because an unsimplified slope helps me figure out where the vertices are. Okay, let's see if we can actually do this. So I'm going to sketch the graph of, all right, clearly this is going to be a hyperbola. And I know that because of the minus sign right there. It looks very, very similar to an ellipse. Very similar. Only difference is the plus and the minus signs. So make sure you pay attention. Look carefully. All right, so what do I know? Well, let's see. HK. I know the center. The center is going to be 3, -4. Make sure you pay attention to that comes from the x and that comes from the y. So I know that. Okay, so let's go ahead and start getting this thing graphed. So go ahead and set up a coordinate plane. Okay, so I've got my center identified. I'm going to go ahead and take a look back at the equation. I know that the x comes first, so I'm opening in the x direction, so I'm going right left to get to the vertices. I also know that I am going to use the number in the denominator of that. Well, a squared is always first. So I know that a squared is equal to 16, which means to find my vertices, I'm going to start at my center. I am going to go right and left 4. Remember, we don't use a squared for our distance. We use a for our distance of 4. All right, so let's see. 3 minus 4 is -1. and 3 plus 4 is 7. So let's go ahead and plot those on the graph. Okay, now let's go ahead and find the foci. So if I want to find those, we need to figure out what c is going to be. So let's take a look back up here. We've got our a squared and our b squared. So I know c squared is actually going to be equal to a squared plus b squared, which means c squared is 25, which means c is 5. Okay. Remember that the foci and the vertices are in the same direction as whoever is showing up first. So it's in the x direction from the center. So if I go to find my foci, I'm going to grab my center. I'm going to go 4 units, 5, in the x direction. Okay, so that's going to give me 3 minus, that's negative 2, and then 3 plus. Remember that this should be further away from the center than the vertices are. So I've got 2, negative 4, negative 2, negative 4, negative 2, negative 4, so that's a focus. That's a focus. This is a vertex. That's a vertex. Okay. Now the asymptotes. I'm going to do y, and you can pull it right out of the equation. It's really kind of magical here. So if you go back up to your equation, grab the y plus 4. Actually, here, let's color code that different. Let's do black. Grab the y plus 4. Ignore the squared. Y plus 4 equals. Leave a little bit of space. We're going to put the slope. Grab the x minus 3. Leave the squared. All you need now is the slope. So if we take a look back, whoever is underneath the y, so this is b squared, is equal to 9, which means b is equal to 3. So the top of my slope is going to be 3 because of rise over run. The bottom of my slope comes from underneath the x. That's 4. But remember, you have 2 of them, plus minus. So basically, here's what we're going to do. So I grabbed my numbers, rise over run, remember. I'm going to go back to my center, and I'm going to use my slope of 3/4. Now, if it could be simplified, I'm not going to simplify it because it actually makes it worse on me. So I'm going to go from my center, I'm going to go up 1, 2, 3, 1, 2, 3, 4. I'm going to plot it in black. What I'm going to do is I'm going to create a rectangle using my slopes of negative 3, 4. So, and I'm going to erase this part, so we'll do this so we can see what I'm thinking. I'm trying to create a rectangle right here. Now, if I do this correctly, both of my vertices are on the edge of that rectangle. That's why I didn't want to simplify. What I'm going to do is I'm going to use that rectangle to figure out where my slope is, find the location of my vertices, and if I did this correctly, the vertices will end up on the edge of the rectangle. Okay, so let's get rid of the rectangle, so it's not necessarily technically part. And I want to graph these lines. So I'm going to start here, here. I am going to dash these in just a minute. These asymptotes create like a boundary where your graph is not going to hit. Okay, now let's give it a quick sketch. So start at the vertices. We know the behavior of a graph when asymptotes are involved. It races to it and tries to hug. The beautiful part about this, we don't have to worry about it hitting the asymptotes. So it's not like rational expressions where we had to do that. So we're going to grab here. We're and erase. Erase. There's our hyperbola. I think we've got everything checked off the list. Okay, another example doing the exact same thing, except now we have to put it in standard form ourselves. So I'm going to rearrange this, and I'm not always going to put the x squared first. I'm going to put whichever of the two is positive first. So my y squared is positive, my x squared is negative, so I'm going to put my y squared first. I'm going to put a plus sign. I always like to have a plus sign between these. Negative x squared plus 2x. And then I'm going to move my 47 to the other side. I'm going to factor out my 16. Here, I am definitely going to factor out a negative, whatever the coefficient is, in front of my x squared. If it was a negative 7, I'd factor out a negative 7. If it was a negative 18, I'd factor out a negative 18. In this case, it is a negative 1, so I'm going to factor out a negative 1. That's going to be x squared minus 2x is equal to negative 47. Okay, consider pausing right now. Complete the square, draw the boxes if you need to, and then remember to keep your equation balanced. When you're ready to come back, go ahead and unpause it and then catch up with me. Okay, so without drawing the boxes, I'm going to go ahead and erase my parentheses. I'm going to extend these down. I know that the number that completes the square for the y's is going to be 4. And then I'm going to make sure that I keep it balanced. So I figure out what I put here. So I have a 16 and a 4. So I'm going to put plus 16 times 4. Plus 16 times 4. That's what I got for completing the square on the x's. Okay, I'm going to go ahead and erase the parentheses, or that was for the y's. Erase the parentheses for the x's, extend those a little bit further. I know the number that completes the square is a plus 1. Okay, so I'm going to do a make sure you pay attention to the sign, negative 1 plus 1. So I have a negative 1 times 1. So that's going to keep my equation balanced. Okay, from here, I'm going to go ahead and write this in factored form. It's going to be 16y plus 2 squared minus 1x minus 1 squared. And then if I do the math on the other side, I'm going to get a 16. Okay, still 1 equals 1. So I'm going to divide by 16, divide by 16, divide by 16. So I'm going to get y plus 2 squared all over. You don't have to write the denominator of 1. I'm going to, just to try to help myself out. And then minus, okay, x minus 1 squared all over 16. And then 16 divided by 16 is 1. All right, center. Just be careful. Remember your center is an x, y. So the x is a 1 and the y is a negative 2. You just got to make sure that you look at the specific locations. Okay, so I've got a 1, negative 2. I'm going to go ahead and pause it and get my graph going. Okay, vertices. I've got to pay attention to who is positive. Well, it looks like the y is positive. So this thing is opening up, down, and it is going 1 unit from the center. This is telling me that a squared is equal to 1, which means a is equal to 1. So the distance that I'm traveling from the center up and down is 1. So I'm going to take my center, 1, negative 2, and I'm going to go up and down 1 unit. Notice that I'm affecting the y value because the y values go up and down. So this is going to be 1, comma, negative 3 and 1, comma, negative 1. Okay, I'm going to go ahead and plot those. 1, comma, negative 3. That is a vertex. 1, comma, negative 1. That is also a vertex. Okay, let's see what our vertices are going to be. Okay, so vertices, let me get my purple pen back, or excuse me, my foci. So my foci, remember this comes from c squared is equal to a squared plus b squared. I want to be further away from the center than a, or my vertices are. So this is going to give me c squared is equal to 1 plus 16. So c squared is going to be equal to 17, which means c is going to be equal to the square root of 17. Okay, so I'm going to take my center. Remember that the foci are in the same direction as my vertices. That was up, down. So this is going to be up, down. So plus or minus the square root of 17. Now, you can write these separately or you can leave it just like that. So to write separately, this is 1 negative 2 plus root 17 and 1 negative 2 minus root 17. Okay, root 17, that's slightly bigger than root 16, so it's slightly bigger than 4. Okay, so from my center, I'm going to go 1, 2, 3, 4, and a tiny bit up. 1, 2, 3, 4, and a tiny bit down. So those are my foci. All right, now I'm going to figure out what my asymptotes are. So remember, go back to the equation. So if I go back to the equation, find my y. It's y plus 2. So I'm going to write down y plus 2. Just copy it exactly as it is. Equals, leave a little bit of space for your slope. And then I have x minus 1. Oh, you could have grabbed it from the original also. It's as soon as you complete the square. Okay, so x minus 1. And just remember that slope is rise over run. Well, the rise is what's under the y, so that's going to be 1. And then the run is whatever's underneath the x. But remember, that's b squared. So b is equal to 4. Don't forget plus minus. So from the center, we can go up 1, 1, 2, 3, 4. Draw your little rectangle. 1, 2, 3. Whoop. 1, 2, 3, 4. 1, 2, 3, 4. Now, if you do this correctly, just as a reminder, if you do this correctly, the vertices are on the edges of that rectangle. If they're not, you made a mistake. It's possible that you could have simplified your slope. Don't do that. That's not a good idea. Okay, let's go ahead and give this thing a sketch. So, your asymptotes. I'm going to erase some chunks here. Start at the vertex, hug. Remember here we don't have to worry about them actually crossing the asymptotes, which is kind of nice. Okay, there we go. Okay, so kind of the reverse. Let's see what you can do. So I'm going to go ahead and start identifying things that I have, and I am going to see if I can identify my A, my B, maybe my C, find my center, but I'm going to put them all in the graph. So when you're ready, give it a pause, give it a shot. When you're ready to come back, follow along with me. Okay, so I went through and I plotted my vertices and my foci on my graph. I know for sure right now that this thing is going to open left and right. So it's going to look something like that. Since it opens in the x direction, I know that the x comes first. So I can go ahead and start getting that ready. So I know I'm going to have x squared minus, it's a hyperbola, make sure it's minus equals 1. Some denominator here, some denominator here. Okay, Center, I can find it right now because it's in the middle between the vertices. So here, my center, well, they have a common y value of 3, so I know that's not going to change. And then dead center between 6 and 2 is 4. So if I take a look back at my graph, there's my center at 4, 3. All right, so minus 4, minus 3. All right, we're almost done. Let's see. To get to the vertex, or each one of them, that distance is going to be A. So from my center to my vertex, looks like A is going to be 2. So if A is 2, then that means A squared is equal to 4. And A always comes first, 4. Okay, C is from my center to my focus. So it looks like C is going to be equal to 3. All right, let's do a little bit of work off to the side. I know that C squared is equal to A squared plus B squared. Okay, so what did I say C was? C is 3. So C squared's 9. A squared we just found out was 4. Subtract. Looks like B squared's 5. And it's B squared that goes in the equation. So just put a 5 underneath there. Looks like we've got the equation.